Hello everyone, welcome to the course Geotechnical Engineering 2. So in this module number 3 and lecture number 12, we will be discussing on the Coulomb's theory. Okay, before that let us now look at the course outline. So if you look at the course outline, initially we have discussed the infinite and finite slopes as well as a terminology known as the factor of safety. Later we have understood the stability analysis methods, and then we have understood the stability of slopes for embankments as well as dams. So now we are trying to understand the concepts of earth retaining structures. So now let us look at the previous lecture. So coming to the previous lecture, we have discussed the Rankin's theory for corrosive soils. So if you look at the concepts that we have discussed, in this case we determined the active pressure. Okay, we determined the active pressure where we have obtained PA, the passive earth pressure, as Ka gamma h minus 2c dash root over Ka. But in case of passive pressure, we have obtained this passive pressure PP as Kp into gamma h plus 2c dash root over Kp. So this is the difference between the active pressure what we have obtained for Rankin's earth pressure in case of corrosive soils as well as the passive pressure. Okay. So coming to the next topic, that is the Coulomb's wedge theory. Okay. So Coulomb's wedge theory is considering the equilibrium of the sliding wedge. Okay, that means if you consider any soil mass, the failure is assumed to be along a certain plane, and if you consider this as a ground surface, and let us say there is a small embankment in this manner and it is in the form of a wedge, that means this failure is in the form of a wedge. Okay, so that is why Coulomb assumed that the failure is along the equilibrium of a sliding wedge. Okay, that too when the retaining wall movement is taking place. Okay, so in the active case, this sliding wedge, whatever that is there, when the wall is moving away, so the sliding wedge is actually moving downwards is considered. And in the passive case, the sliding wedge is assumed to be moving upwards. That means in case of active case, it is assumed to move downwards, and in case of passive case, it is moving upwards. So to maintain the wall in the equilibrium and the wedge in the equilibrium state, so whenever this sliding wedge is moving downwards, to resist this, an equal and opposite magnitude is acting along the surface. If you consider this as a surface, then obviously along the surface, if it is moving downwards, then resisting force is offered by the soil in the opposite direction to maintain the soil in the equilibrium. Okay, now let us now consider the analysis of such type of wedge failure, and in this case the analysis is carried out considering the limit equilibrium method. Now, so for this the following assumptions have been made. So the first one is the backfill is generally dry as well as cohesionless, and it is considered homogeneous and isotropic and ideally plastic. Now the other one is that the slip surface is assumed to pass through the heel of the embankment, and the wall surface is assumed to be rough. The sliding wedge is actually acting as a rigid body. The sliding wedge is actually acting as a rigid body, and for this case the magnitude of the entire earth pressure is obtained by considering the equilibrium of forces. Okay, it is considered by equilibrium of forces that is acting on the entire wedge. So now let us discuss the Coulomb's theory of analysis. Okay, now for this let us consider a certain embankment in this manner which is inclined along one side. Okay, let this angle be beta. Okay, let the height of the embankment be capital H. Okay, let us assume the ground surface is actually inclined to the horizontal at an angle I. Okay, so I am assuming the ground surface is actually inclined ground surface is actually inclined at an angle I to the horizontal. So let this surface angle be beta, and let us assume there is a failure plane in this manner, okay, which is inclined at an angle alpha to the horizontal. Okay, so let us represent this as A and this as B. Okay, now let this be D, and to maintain this structure in equilibrium, okay, this wedge ABD must be in equilibrium to resist the failure. So let us now consider the entire forces acting on this particular wedge. Okay, so the first one is the weight of the structure. Let W be the weight of this particular wedge which is acting in the downward direction. Okay, and let R be the reaction which is acting on this particular slip surface, and let PA be the pressure that is acting on the retaining wall which is resisting the entire wedge. Okay, so let me just draw the normals to this particular line. Okay, and let us say this is the normal to this particular line. So this angle is 90 degree and this angle is 90 degree. Okay, so let us consider the equilibrium of forces, and let phi dash be the angle here which the resultant is making with the normal to the slip surface, and let this angle be delta. Okay, so let us try to consider the equilibrium of forces here. Okay, so in this particular wedge which is trying to move down is actually resisted by the soil present in this particular region. Okay, so we have considered the equilibrium of forces. For that, the weight of the wedge that is acting downwards is represented by W, and the resisting force that is acting normally is taken R, okay, by the soil, and the reaction or the resistance offered by this particular embankment to the soil is represented by PA, which is resisting the movement of this particular soil mass. Using the law of sciences, that is law of science, okay, here PA by, okay, this is PA. So if we draw the equilibrium of forces here, let PA be in this particular direction. This is PA. Okay, W is acting in this direction, and let the reaction be acting in this particular direction, capital R. Okay, so we need to know these angles. Okay, so this angle is alpha minus phi dash, and this angle is xi minus beta minus delta, xi minus beta minus delta. Okay, so considering the law of forces, this particular force PA by sine of alpha minus phi dash is equal to W by sine of 180 degree minus beta plus delta minus alpha plus phi dash. Okay, so by considering the equilibrium of forces, this will be 180 minus beta plus delta minus alpha plus phi dash. Okay, so this is this particular angle. Okay, this is 180 minus beta plus delta minus alpha plus phi dash. Okay, just try to obtain this from the equilibrium of forces on this particular wedge. Okay, if you consider the angles here, the angle between these two planes is 180 minus alpha plus beta, and this entire angle, okay, if you bisect this particular side perpendicularly, so it will be 90 minus alpha plus I, this particular angle, and similarly this angle is alpha minus I, and this is 90 degrees. Let us say this length, let this be E. So AE is one particular line here. So if you consider the weight of this particular wedge W, that is half into base is length of this particular wedge, here it is BD. So it is BD, okay, multiplied by height AE, half into base into height, that is the area, into its unity, since it is considered in a two-dimensional plane, so it is into 1. So we got the volume, so multiplied by the unit weight gamma. So let us represent for time being, this is half into, let this length BD be L and AE be the height. Let us represent this by M, and this is gamma. Okay, so the weight of this particular wedge is represented in this manner, that is half Lm gamma, where L is the length of this particular failure wedge and M is the height. Let us represent this particular distance L as this DE plus EB. Okay, so length L is represented by DE plus EB. Okay, so from these two triangles, this is one right angle triangle and this is another right angle triangle, AED and AEB. So from these two right angle triangles, let us try to obtain DE and EB. So from this particular triangle, we may also obtain M. Okay, from triangle AED, M may be obtained as AD into sine of beta plus alpha. From this particular triangle, M may be obtained as AD into sine of beta plus alpha. Okay, and similarly DE may be obtained as M sine alpha plus beta minus 90 degree by sine of beta plus alpha. Okay, similarly this length DE from the triangle, it may be obtained as M sine of alpha plus beta minus 90 by sine of beta plus alpha. And this length EB may also be obtained in a similar way, M into sine of 90 degree minus alpha plus I by sine of, this will be this particular angle, alpha minus I. Clear? So in this way we have obtained DE and EB as well as M in terms of beta, alpha and I. Okay, and here AD. Okay, so we need to find out the length of this line AD. So if you consider this particular triangle here, so we know the height as H and this angle is beta, so obviously AD is the sloping surface, so this will be H by sine beta. Okay, simply AD will be H by sine beta. So we have obtained all these expressions, so simply we can substitute in this. Okay, we know what is Lm, so if you substitute in this equation number 1, let us say this is equation number 1, so if you substitute in this equation 1, finally we can obtain the W. So now after obtaining these values, we can obtain the value of PA as W into sine of alpha minus phi dash by sine of 180 degree minus beta plus delta minus alpha plus phi dash. Okay, so PA can be obtained by this formula, and we know the formula for W as well. It is W is equals to half into L into M into gamma. We know L, M and gamma, so substituting this W in this equation, finally we can obtain the value of PA as half into H square gamma sine of beta minus alpha whole square, sorry this is beta plus alpha whole square, divided by sine square beta multiplied by sine of alpha minus phi dash by sine of 180 degree minus beta plus delta plus phi dash minus alpha. Okay, this is one term, and whole multiplied by sine of beta plus alpha minus 90 by sine of beta plus alpha plus sine of 90 degree minus alpha plus I by sine of alpha minus I. Okay, so this is the final expression what you will obtain after substituting the value of W in the earlier equation PA, as well as we know LM what we have derived. So substituting this, you will obtain at the final expression of PA, that is the passive earth pressure, where this entire term can be represented by the coefficient of active earth pressure. Okay, so the similar procedure is repeated n number of times, and a similar values of PA are obtained for different levels. Okay, so the value of PA what we have observed now is obtained for different levels by assuming different angles. Okay, we will obtain a different line of this particular passive earth pressures. Okay, this will be observed for different angles as a curved line. So now let us move on to the next topic. So that is, we will be discussing the Coulomb's active pressure theory in case of cohesive soils. So this particular theory given by Coulomb in the form of wedge can be applied to the cohesive soils as well. Okay, but here earlier we have considered the three forces. Okay, to maintain the wedge in equilibrium we have considered three forces. One is the wedge weight, that is self weight of the wedge, that is considered W, and the other one is the reaction force on the particular sliding wedge or the failure wedge, that is R, and the other one is the passive resistance that is offered by the particular body considered against the wedge, that is PA. So additional to this, when we are considering a cohesive soil, there are two more additional terms, that is cohesion force as well as the adhesive force. Okay, cohesion force is represented by C and the adhesive force is represented by CA. So as discussed, so there are some additional terms here. So if you consider this particular diagram what we have seen earlier, okay, let this angle be beta and let the ground surface is inclined at an angle I, okay. So let the failure wedge be this region, let this be a straight line, let this be A, B and D, and let this be inclined at an angle alpha. Okay, so this is the wedge that we have considered. So in case of cohesive soils, as usually we will be considering the self weight W, okay, and let there be some passive resistance PA, okay, and let there be the reaction force R, okay, offered by this particular wedge. So apart from this, in this particular case there is additionally another force due to cohesion, that is C is the cohesive force along the sliding wedge and CA is the adhesive force along the considered resistance offered by this particular body. Okay, so these are the two additional terms, CA and C, what we considered in this case. So for the equilibrium of forces, we have to consider this PA acting in this direction and this weight, self weight of the body that is coming downwards, and the other force, that is the reaction force, which is in this direction R. Apart from this, there are two more forces, so these have to be considered. One is the CA, that is along this particular direction, okay, and the other one is C, okay, this is C along the other direction. So this is the equilibrium of forces diagram that we have. Let us say this is the forces representation in equilibrium. That means to maintain the particular wedge in equilibrium, we have considered this particular diagram. So in a similar fashion, what we have observed earlier, the derivation may be carried out for this particular case as well to find out the value of PA. Apart from this, coming to the passive pressure PP, okay, coming to the passive pressure, this can also be obtained, okay. Similarly, the passive earth pressure, okay, can also be obtained for cohesionless soils as well as cohesive soils. However, let us look at what we have for cohesive soils. In that case also, the value of passive pressure PP is given by half into gamma into H square into Kp, okay, where this particular entity Kp is actually given by sine square of beta minus phi dash by sine square beta into sine beta plus delta whole into 1 minus of root over sine of phi dash plus delta into sine of phi dash plus I, okay, divided by sine of beta plus delta into sine of beta plus I, okay. So this is the expression what we will get while deriving it for passive earth pressure, okay. Just note down the equation, that is quite sufficient, okay. Now in the upcoming lecture we will be discussing on the shallow foundations. So we will be discussing on the shallow foundations, which is quite important for us, okay, where we use the bearing capacity and we try to understand the concept of the shallow foundations as well as different foundations in the upcoming sessions. So that's it for today. I hope you have understood very well. Thank you very much. Have a nice day.